So in this series of lecture, we'll discuss about the phase lock loop or the PLL. So PLL is a very important block in a system on chip. So in fact, every chip, every digital chip, or every chip that we see will have a PLL because the digital blocks need a clock, and the clock in a chip or in a system on chip is provided by a PLL. So let's try to understand more about that. So PLL, phase locked loop. So the first question is, why a PLL is required? From the system on chip perspective, why a PLL is required? So a PLL is required for frequency multiplications. So let's try to understand. So it is used So suppose I have a system on chip SoC. Okay, so of course nowadays the digital blocks in an SoC may be operating at gigahertz frequency with the advancement of the technology, or with a very like a very advanced technology node. So the SoC will definitely work in the gigahertz range. So the clock frequency is in the range of gigahertz. Okay, but but the clock that is provided generally, which comes from a crystal oscillator, is only in few megahertz range. So this is my SoC. So in a PCB externally there may be a crystal oscillator. So this is a crystal. It's a crystal oscillator. And a clock from this crystal is fed to this SoC. Okay, this is a crystal oscillator, and the clock frequency of this is generally in the megahertz range. So basically I need to multiply it, right, by n times. Suppose I need a 10 gigahertz clock here, and it is producing maybe 10 megahertz, right? So definitely I should multiply it by 1000 times. Okay, or like if it is 1 gigahertz, and if it is 1 megahertz, then of course it's also 1000 times. So I need to multiply the clock frequency that is coming from the crystal by n. Okay, so the question may arise is, why can't we generate gigahertz clock frequency itself? Why do we need a clock multiplier? Of course the multiplication doesn't happen outside. The multiplication happens inside the IC. There will be a PLL block here, right? So, and then this will multiply by n times. N can be, as I was mentioning, this n can be of 1000 or more than 1000, right? So this is my PLL block, right? So the clock that is this PLL will be providing to the SoC, the digital circuits, will be multiplied by 1000 times. So why can't we get a gigahertz clock directly? So the reason is that the crystal oscillator generally operates in the megahertz range. The crystal oscillator operates in the megahertz range. So this is one of the main reason. And of course, we can also design oscillator inside the SoC itself. But the problem is with the purity of the frequency. I mean, the frequency is noisy, whereas the frequency that is generated by crystal is very pure, just like we use in watts and all the crystal. So the crystal is very pure, whereas the the VCO that is there inside the SoC, that may be noisy. In fact, a PLL, one of the main purpose of using a PLL is to even reduce the noise of a VCO or a free running oscillator inside the uh, in a PLL or inside this chip. Okay, so the other application of the PLL is that noise filtering of an oscillator. Okay, so even if I build a oscillator, right, there are different kinds of oscillator, right? We know that from the basic electronics classes, we know that there may be a phase shift oscillator, and so generally what is expected is that this oscillator should generate a particular frequency, something like this, a frequency tone, maybe let's call it maybe 5 gigahertz. Okay, but it is not clean like this. It doesn't just oscillates at a particular frequency. If we draw the frequency spectrum, because of the device noise and many other things, it will have some this is band of another frequency that is coming up. Okay, so which is not good. Okay, so but with the help of the PLL, we can filter out and make this make this we can shape it and make it very sharper. Okay, make it operate on only at a particular frequency, so we can filter out this noise. So this is one of the application of the PLL. Okay, the other application, very important application of a PLL, is clock recovery in serial links. Serial link communication. So the information that is sent by the information sent by the serial links, like for example the HDMI cable, HDMI or PCIe or PCI Express, PCIe, it is also called PCI Express, right? Or maybe the high speed USB, right? We have the USB 3 and up, right? So all these the communication link, they only send the data bits, they don't send the clock frequency or the clock corresponding to a data. Okay, and of course we know that any bit, right, any bit information, if it doesn't have the clock information, we will not be using, we will not be able to use that digital bits, right? So we need the information of the clock if we want to use any data information that we are receiving. So and in many of these applications it is not possible to send clock along with the data. The reason is because we need separate cables, and there are many other reasons why this communication links doesn't send clock along with the data. So as a result of which, we are supposed to recover the clock information from the data itself, and this is done again done by of course a modification of a PLL, or it's as a PLL. Okay, and the next one is the, if I want to synchronize multiple clock source, right? So if I want to synchronize multiple clock source, then also we use PLL. So I have a single source, and the multiple, multiple oscillator can be synchronized using a PLL. Okay, so let's try to understand the principle of the PLL, how it works as a clock multiplier. So what we mean by a clock multiplier is something like this. So I have a PLL here, and suppose I am providing a clock here as an input clock. So this is my input clock, and this is my output clock. Okay, so input clock, if it is something like this, okay, so if I have a multiplication factor of maybe 2 cross 2, so it should give me twice the frequency. Okay, so basically my time period gets half. So this is the basic meaning of frequency multiplication. So if I have a the input has a this time period tp, so then the output will have a time period of tp by 2. So this is the multiplication, 2 times multiplication, and of course if it is 4 times, this will become by 4, like that. Or the frequency, if we see in terms of frequency, it will be 4 times. Okay, so now how do we get this kind of multiplication? Okay, so to understand the basic operation of the PLL, we'll try to understand how does we can get a multiplication in a voltage domain. Okay, so we generally use op-amps to design amplifier. Okay, so op-amp works on the principle of the basic feedback circuits. So in the introduction to electronics classes, we must have learned that how if I have something like this, negative feedback, and so this is my R1, this is my R2, and of course this is ground, and this is my V in, and this is my V out. Okay, and we all know that the this is a non-inverting amplifier. Okay, and V out by V in is given by 1 plus this is R2 by R1. Okay, and this will be, I should say that 2 if R1 is equal to R2. So I'm just giving an example. Okay, so so yeah, so this is how the feedback circuit works. Okay, so basically what I do is I will feedback the output to the input, and of course here we have a division that is happening. The output voltage is divided by 2 here. So okay, so so basically that's why the input is becomes 2 times compared to the output. Okay, so this is how the feedback works. Okay, so to understand more clearly, let's try to draw a generalized diagram of the feedback circuit. Okay, so so suppose I have this feedback network. Okay, so I have the gain part. Okay, suppose I have an amplifier of gain A, and this is my output one, and the output is again fed back to the input through a feedback part, and we know that it's generally represented by the beta. Okay, so this is a very common thing in the control systems or in the signal systems. Okay, and then we are going to feedback this to the input, and so, and of course this is my input. This is my V in, and this is my V out. Okay, and of course the the feedback is subtracted, or the output is multiplied with a feedback factor, and then it is subtracted, the input is subtracted from that. Okay, and we know that from the basic classes, we know that V out by V in this case is given by A by 1 plus A beta. Okay, and if A is very large, this is almost equal to 1 by beta, okay, or I should say that no, for A is very high, okay. So so basically what it means is that, so I need to subtract, or I need to compare the input with a beta times of these, you know, output, okay. So this is what I'm supposed to do. And of course we know that in a feedback circuit there is an error voltage VERR, and the purpose of this VERR is that we want to make this error voltage as small as possible, okay. So yeah, so here also what we try is that we try to make these two, you know, these two voltages very close, right? So this is the basic, you know, I should say that the basic the way by which the feedback is implemented, that, you know, that we try to make these two voltages very small. Basically we are comparing these two voltages and trying to make very small. Similarly here also we are trying to make this error voltage very small, okay. And of course suppose if I want to get a gain of 2, that this beta should be half, right? Beta should be half. So basically what I'm trying to do is that I'm making the output half compared to, you know, or I'm making the output half before it comes here, so that I can compare with the input, okay. So what it means is that if my beta is half, okay, if I want to get a gain of 2, so my beta should be half. So then, you know, so then this will be, you know, V out will be, you know, this will be B out by 2, okay, and this B out by 2 will be compared to the input, and such that the error is V in minus V out by 2 is almost 0. That means my V in will be approximately equal to, you know, half of the V out, or we can say that V out by V in is equal to 2, okay. So this is the basic, you know, this is the basic principle that we are going to use in a PLL design, right? So if I want to get the output to be n times higher than the input frequency, if I want it to be n times, that means I'm supposed to divide that frequency by n times and compare with the input, and make sure that the comparison is such that the n times of the output and the input, they are almost same. And if I'm able to make that, then I'll get my output which is n times higher, okay. So this is the basic principle. Just like we are doing for this voltage, we are also going to do for the frequency as well. Yeah, so let's try to formulate it, whatever I'm telling this one. So let's try to write it down, okay. So suppose this is my okay, let's use some other color, shaded color, okay. So this is my PLL block, okay, and I have my input here, okay. So this is my input that is coming inside the PLL, some frequency, okay, input maybe, and of course I want this output, okay. I want my output here, and the input frequency is n times higher, okay. So if the input frequency is f in, then the output f out, I want it to be n times f out, sorry, f in, okay. So this is my goal. So just like in the amplifier design, we want the gain to be some a times, you know. So again, so what I need to do is that whatever the output that I am going to get, I have to compare with my f in by, after dividing it, you know, by n, okay. So my f out will be equal to f in if I divide it by n. So what it means is that in the PLL we'll have one block which is called a divider block, and this will divide by n, divide by n, the frequency will be divided by n, and I will try to compare this one, whatever I have got here. I have some block here which will compare which will compare these two, right? Whatever is coming to, so here what I have the frequency here, it will be f out by n, and I will try to compare these two, and if I can make sure that these two are the same, right, then I will be able to log the output at f out equal to n by f in. Okay, so the first block of a PLL is called the phase detector, okay, PD. So PD stands for a phase detector. So what it does is that it tries to detect the phase difference, okay, between these two, and it will try to give its output, which will have the information that whether the phases of these two are same or not. So now, of course, the question may come, like we are trying to make the frequency n times higher. Why we are not using a frequency detector and trying to spit out this information instead of a phase detector? So what we will see is that if we can make the phases of these two signals the same, we'll see that automatically the frequency is also going to be the same. So this is what we are going to see eventually, okay, whereas the vice versa is not true. So if you can it's become difficult to make this two frequency the same. So this is what we'll see eventually, okay. So for time being, just try to understand that this PD is trying to compare the phase of these two, and will give an information out where and that information that output will have the information that whether the phases are same or not, okay. So let's give an example, okay, for this. So before going to the example, so basically we are trying to do the same thing here. We are trying to the output is divided by 2, and we are trying to compare these two, and then when these two are almost the same, we know that the output is 2 times higher than the input. Or similarly here also, we are trying to make the error voltage very small. So same principle we are trying to use in the PLL. So now yeah, let's try to understand about this PD block more in details. So let's zoom into this PD block and try to see how it works, okay, and its characteristics, okay. So we will discuss about the phase detector. PD. So let's try to understand the properties of a PD first. So this is my PD. So in PD, I will have two inputs definitely. Let's call it as V1T and V2T. And we have this output, okay. Okay, this is the output of the PD, okay. So now what it will try to do is, right, so this is the characteristics of the curve for this PD, okay. So if there is a phase difference between the input of V1 and V2, okay, let's call it maybe as pi, okay, delta pi, which is the phase difference between these two, then it will speed out some voltage, okay, and the let's call the output of the PD as BPD instead of just V out, okay. So the average value of this output, okay, the average value of this output, so what I'm supposed to get something like this, okay. The x-axis that I have here is the radians, okay, and the y-axis I have is in the volts, okay. So it will spit out a voltage if there is a delta phi difference between the phases of V1 and V2, okay. So let me draw a diagram, then it will be more clear, okay. So this is my V1T and this is my V2, okay, and we can see that there is a bit difference in the phases, okay. So this is the delta pi. Okay, so delta pi is the I should say that phase difference between v1 and v2. Huh? So let me write down. Delta pi is phase difference between v1t and v2t. Okay. Okay, so now to define these characteristics of this phase detector or the PD, there is an important concept that comes is basically the slope. Okay, the slope of this line. Okay, so the slope of this line is defined as the KPD. Okay, so this is called as the KPD. So KPD is basically how much the slope of this line. So the slope, or I should say that this is basically the slope, and its unit is unit of KPD is, we know that it is y by x, so it is volt per radians. Okay, so how much voltage this PD is producing for a phase difference. So generally what happens here is, if the phase difference is positive, it's going to speed out positive voltage, whereas if the phase difference is negative, it will speed out a negative voltage. So this is the basic property of the PD. Okay, so we can see here in this PD that depending upon what is the phase difference, it's going to speed out a particular value of the average voltage. Okay, and and this unit, the KPD, okay, which is the slope of this line, defines that how much voltage, right, whether it is very sharp. So it defines the gain of this phase detector, right? Whether the voltage is very high, like even for a slightly phase difference, some PD can produce a very large, output average voltage. Okay, so this PD. Now, if I want to implement this PD with a maybe simple digital circuit, right? So we can think of what digital logic can be used for a PD. So here the main importance is that, like, if there's a high phase difference, my this average PD should, or I should say this average voltage should be very large. Whereas if my both the phase for the clock are almost the same phases, it should be very small, right? The output of the PD, the average voltage should be very small. And the only logic which satisfies this condition, right, is basically a JOR circuit. Okay, so using a JOR, I can easily implement a phase detector. Okay, so JOR can be used as a phase detector. Of course, there are more advanced phase detector that we'll learn eventually. Okay, but the basic one, you know which we can use, is a JOR circuit. So here I have V1T, okay, and V2T, okay, and of course we have the VPD T, okay, and this JOR will speed out. Okay, this JOR can speed out whenever there is a difference in the phase between these two. It will speed out a logic high. Else if both of them are same, it will speed out logic 0. Okay, so let's see this one. For example, in this case, when both of them are 0, we know that the output of a JOR is 0, and whenever there is a difference, like this is 1 and this is 0, it will speed out a 1 here. Okay, similarly here also. Okay, because I can see here that this is 1 is 0 and 1, so there's a difference, so it will speed out this voltage. Okay, so similarly again here also, it is supposed to speed out the this logic. Okay, Okay, so something, this is what will be the output of the PD, and we can see that if I increase the phase difference, it will increase. Okay, and of course, this two, this output will become maximum. No, this is the VPD. Okay, and it becomes the maximum. The average value of this PPD will maximum. We know that when this, if I move it and it goes, it goes by pi. Okay, sorry, pi, and no, so this way, and of course, as we move on and it becomes 2 pi, then again these two waveforms will become the same, and then the BPD output will be the same, will be 0. Okay, so we can draw the characteristics of this one. So if you try to draw the characteristics of the PD of this JOR gate, it will look something like this. Okay, so this is the average value of the PD. Okay, so now when both of them are same, so maybe let me copy this one. So when both of them are same, right? When the phase difference is 0, this is almost 0, but it becomes maximum when it gets inverted. Of course, sorry, there's a little difference in the duty cycle. So here, what we are assuming is that the duty cycle, is 50%. Okay, so what it means is that when the phase difference is 0, my BPPD is PPD is the average value that is spit out is 0. Okay, whereas as it increases till pi, right, where pi means both are this is a V1, V2 is an inverted version of V1. Okay, so then it will be maximum, and again it decreases as as it goes on like that, and it becomes 0 again at 2 pi. Okay, so it continues, it's a periodic. Okay, similarly this side also it is something like this. So it reaches the maximum value, the BPD, the maximum, the average voltage that is spit out by this PD becomes again maximum when it is minus pi, and then again it goes to 0 when it is 2 pi. Okay, so this is the characteristics of this PD with a JOR gate. To understand this concept and all the PLL in a very properly, and to appreciate its concept, it's always good to do simulations. So we will be using a simple platform of LT-Spice for doing the simulation, starting from very basic. So this will help us to understand the basics very nicely. So let's try to realize this PD, and try to see it. Okay. So this is my LD-Spice platform. Of course, this is in the Mac platform, but the platform looks quite similar in the Windows. And LD-Spice, you can download it from analog devices. So yeah, website. So it is free to use, and it is an open source. Okay, but it's a very powerful tool to do the simulations. For the basic things of how to do the simulations and all, you can go to any tutorial. There are many tutorials, because this is a very standard tool. Okay, so to do that, let's first draw our JOR. Okay, so do the right click and go to the draft component, and here you can search for the digital circuits. So if you see here, in this here we can go for the digital circuits, and we want to go for a JOR, or you can simply type here JOR as well. Okay, so this is my JOR. Okay, so of course here this is a multi-input JOR, more than 2 inputs, but we will be using only 2 of them, other will not be using. Okay, and here we have an output here, and of course the output bar. Okay, so we will not be using this one output bar, we'll only be using this output. Okay, so yeah, so this is my JOR. So now let's try to I should say that let's try to get input voltage sources. Again, go right click, draft components, we'll use voltage sources, VOLTAGE, or you can just search here. Okay, so just put 1 here and 2 here. Okay, So now we need to do the connections. So for doing the connections, you can again right click, draft wires. Okay, of course, in case of the Windows, you can have a shortcuts as well, so which we can see at the top. Okay, and here we will use something like this. Okay, and yeah, and of course the output again, the draft wires. Okay, so click here and get it here. Okay, escape. So if you want to disable any command, you can just try escape. So again, draft wires. Okay, so here, okay, so now I need to put a ground here, and of course I need to put an output port here. So draft net. Okay, so we can use a ground here. Okay, so I use a ground here as well as here, and for the output, maybe edit, delete. We'll delete this one, and draft. So we'll go for a port. Okay, this will be an output port, so just name it as OUT or basically BPD. Okay, that will be more better. Okay, so yeah, yes, so we are almost done. You can leave this wire hanging, or we may connect it to the ground. Okay, so yeah, so let's edit this one. So let's edit the property of this one and make it a voltage source, or I should say that it's a pulse generator. Okay, so if I go here and I can select different options, pulse generator. So initial value, let it be 0, then it is 1, then there is no time delay, 0, and T rise, let's make it as maybe 10 nanosecond, and T4 let's make it 10 nanosecond, and T on let's make it 1 microseconds, 1 U, and T period 2 microseconds, cycles no need to write. Okay, so basically this is a this is a T period of 2 microseconds, so it's a 0.5 megahertz. Okay, so similarly I'll try to give the similar input here. Okay, so right click and go to advanced, and click here as pulse sources. Okay, again this will be initial value 0, and this is 1, delay. Okay, so we need to put a delay here so that we can see there is a difference. So we'll put in terms of microseconds. Maybe let's start with 0.1 microseconds. T rise again will give as same as this one. So here there we have 10 nano, T4 10 nano, T on again it is the same, 1 micro, 2 micro. Okay, so yeah, so we are done. So these two are similar. Okay, there's a slight overlap in the this one, so if you want we can move it a little bit, this one. Yeah, it's overlap with this naming of V2. Okay, great. So let's again level this wires as V1, V2 as well. So again right click and draft and net name as V1. Okay, and this as draft, net name as V2. Okay, so yeah, so this is V1, V2. Okay, so I'm almost done. So yeah, so what we'll do is that we need to do a transient simulations. Okay, so go to right click and maybe draft spice directive, then again right click here, help me edit analysis command. So I'm going too fast. If you have an issue, you can always pause the video and rewind it again and see it. So transient analysis we are going to do. So our time period is 2 microseconds. So maybe if I want to see maybe 4 cycles, I should make it 8 microseconds. Okay, So yeah, so this is my transient simulation. Okay, so this is my spice directive. I just need to put here. Okay, so now let's run it. Okay, so you can see this waveform that will be coming. So here I can plot. So I can plot my v1, v2. So that my mouse cursor will be sent to this kind of probe after doing the simulation, and this. So if you go here, you can see here. Okay, so of course the graphs are overlapped, so it's very difficult to see. So what we'll do is that we'll try to split them. So add plot plan. Okay, add plot plan. Okay, so what I'm going to do is I'll put the PD here and v1 and v2 here. So I will add traces. So here I'll get v1. Okay, this add traces here. I'll go at the v2, and here I want to plot only PD, so I need to delete this v1 v2. So what I can do is delete. So delete this one, delete this one. Okay, so you can see here. So it's like, so as we have seen that because of this phase difference, it's a simple XOR operations, no big deal. So we can see that because of this phase difference, and this is large. Okay, so because of this phase difference, we can see this output is 1. Okay, and as we increase this phase difference, so currently we have just little bit, which is here, this we have given it as a only 0.1, right? So if we shift it by, because the this time period is 2 and the on duration is only 1 microsecond, so if I shift it by pi, right, shift it by pi, which is equivalent to the delay will be 1 microsecond. Okay, so we can edit that. So if let's edit this one, right click, so we will make it 1 microsecond. So 1 microsecond. So, or to see that 0.5 first, or let's make it 1 microsecond and see what happens. So the delay is 1 microsecond. So if you run it, right, so we can see that almost it is it is high, right? The average value of this PP is very high, and it's almost high, right? It's almost staying 1, because you can see that these two are almost the difference between them is pi. Okay, and of course as I keep on increasing the delay and make it 2u delay, it's delayed, one waveform is delayed by 2u. So you can see that again, it of course here this is the initial point, so there was no waveform, but you can see here it's almost 0. Okay, yeah. So to look the plot better, we can make this grounded input, then at least look wise we can see that it's more clean. Otherwise you can leave it hanging also, it's fine. So what we'll do now is we'll use a net name ground. Okay, so we'll just put it like this. Okay, if you run it, you're supposed to get the same result. And if you make it again to the original of 0.2 micro, so we should get the same XOR output. Yeah, you can speed out the average value of this one also by just press Control, hold it, and then just click it. So as soon as you see, you can see that for an interval from 0 to 8 microseconds, the average value is 99 millivolt. Okay, so from this also we can find out the the KPD. Okay, so if we know the phase difference, the ratio of the phase difference, like for this phase difference, how much it has speed out. Okay, that we can find out. Okay, so from this we can easily find out the KPD. Okay, with this we'll end the introduction on PLL and also the PD discussion on the phase detector. In the next lecture we'll discuss about the VCO.